So I'm going to show you how you can use trig subs to find some antiderivatives. This is not a quick process, so be warned. So when we might think to do this is if we have, and they don't necessarily have to have radicals, but an x squared plus or minus an a squared. So maybe you've done this before, or you remember from differential calculus, right? These usually lead to triangles. So if you have x squared plus a squared, the triangle that you have looks like this. And we let x, so this is the substitution that we're going to make. We're going to substitute for x a times tan theta. So I have drawn the triangle, so theta, right, is your angle, and I've labeled my sides so that the tangent of theta, right, so tangent of theta is x over a, and that's opposite over adjacent. Okay, so I have those sides labeled, and if I wanted that third side, right, Pythagorean theorem would tell us that it's x squared plus a squared, right? So you should always, that missing side should relate to the form that we're using to substitute. Okay, so when we see this form, we might try, as long as there's not a u sub hanging out there, be careful, right? It's a fabulous calculus teacher's sneakiness is that we'll have a whole bunch of these trig sub problems, and then we'll sneak in one that could be easily done with a u sub, so watch out for that. Okay, so back here, if we see x squared plus a squared and we don't have something else nicer, we say, okay, well, let's try a trig sub. So x equals a tan theta, and then dx, we take the derivative of x here, so that would be a secant squared theta d theta. We'll make all of that substitute, and then we'll just hope that something turns out nicely. Okay. If we had a squared minus x squared, well, that substitution we make is x equals a sine theta. So I've gone ahead and labeled that triangle. So sine theta is x over a, and sine is opposite over hypotenuse. Okay. And then finding your missing side, again with Pythagorean theorem, you'll see the a squared minus x squared square rooted. So now if x is a sine theta, that makes dx a cosine theta, d theta. And finally, if it's x squared minus a squared, that's when we have to make the substitution x equals a secant theta. So secant theta, so I'll give you just a little bit more on that one. So secant theta then would be x over a, but secant theta is 1 over cosine theta. So if I do the reciprocal of both sides, right, that's kind of how you can think of labeling that triangle. So cosine of theta is a over x. Okay. So now back to the secant though. So if x is a secant theta, dx would be a secant theta tangent theta d theta, right? And you might be thinking, well, how in the world would making those kinds of substitutions make anything look better? Well, you know, it might not look better, but it might at least be doable. So let's take a look at this first example. So I'm integrating x squared over square root of 25 minus x squared dx. So, right, your first guess, since we have an x in the top, you might be hoping that there's a u sub in there. So if we let u equal the radicand, right, which is our typical go-to, then my du would be negative 2x. Well, I've got too much. Right? So I can't ignore that extra x that I have up there. You can't just pretend like it wasn't there and it's like, oh, I'll just multiply it in at the end. Right? We can't integrate products unless we do something special like parts or a trig sub. So trig sub is what we're going to try on this one. So it's the 25 minus x squared. So this is an a squared minus x squared. So we're in this option here. We're going to let x equal. So our substitution, x is going to be a is going to be 5 sine theta. So then dx will replace with 5 cosine theta d theta. And I'm going to go ahead and draw my triangle right here because I know I'm going to need it at the end. I'm also going to need quite a few identities. So if you need to brush up on your trig identities, you might have a little cheat sheet going. So let's go ahead and label the sides of our triangle. So sine of theta is x over 5, missing side, 25 minus x squared. Okay, so I'm all set up. I'm ready to rewrite my integrand in terms of theta. So I'm just going to replace everybody with its substitution. So I'll do that over here, and then I'll come down because I think it's going to get quite big. So x squared, so 25 sine squared theta, dx, careful, dx is 5 cosine theta d theta, so times 5 cosine theta d theta. Now I'm on the bottom, so now I have the square root, 25 minus x squared, and x was 5 sine theta, so 25 sine squared theta. Okay, so that looks okay. I mean, not awesome, but here we go. So we're going to come on down here. I'll go ahead and do the multiplying up there. So I have 125. Yes, you could move that out front. That's totally fine. Sine squared theta, cosine theta, d theta. I know it's screaming u sub, but we can't because we have that stuff in the denominator. So let's talk about that stuff in the denominator. Let's do it over here. So I've got the 25 in both of them. So you could think of that as a 25 times 1 minus sine squared theta. And 1 minus sine squared theta is cosine squared theta. And that's all under the square root. And now that I've got it so that it's not a minus under the square root, so it's just one, right, one term under there, now I can actually do that radical. So now we'll do that. So the square root of 25 times cosine squared theta is 5 cosine theta. Okay, well this looks much better because, right, I can get rid of the cosine thetas and I can get rid of one of the 5s. So now what I need to integrate is 25, I'll go ahead and move it out front, sine squared theta d theta. Great, still not done, right? Because we don't know the antiderivative for sine squared. So that means we need to use our double angle formula to get this down to a linear factor of sine. So sine squared theta, remember, is 1/2, 1 minus cosine 2 theta. So we'll go ahead and make that change. So 25, I'll go ahead and take that half and move it out here underneath my 25. So now I'm integrating 1 minus cosine 2 theta d theta. Okay, that one we can do. So here we go. 25 halves. Integrating 1 with respect to theta is just theta. And integrating negative cosine 2 theta. So I'm going to do my little u sub on the fly there because I have a 2 theta, not just a theta. So I'll have an extra half out in front. So minus 1/2 sine 2 theta. And we're done. We have the antiderivative. And we could be all the way done except, right, we were asked to integrate with respect to x. We've got thetas here. So now we have to get back to x's. So let's go ahead and take a look here. So theta, so remember x equals 5 sine theta. That means that sine theta is x over 5, which means theta is the inverse sine of x over 5. All right, so that's going to be my first term. That's what theta equals. So 25 halves times the inverse sine, arc sine if you prefer, of x over 5, minus 1/2. Now I have the sine of 2 theta. Got a triangle here, but I don't have a 2 theta, I only have a theta. So now here's another identity. I'll go ahead and put a box around this. Here's the one identity we used. Here's the next identity. Sine of 2 theta is 2 sine theta cosine theta. You're going to get better at these identities because they're going to keep showing up. Until then, if you want to make yourself a sheet for these ones that get used a lot, you're going to save yourself some headache. Okay. So here we go. So the sine 2 theta is going to be replaced with a 2 sine theta cosine theta. So 2 sine theta, cosine theta. I know I still have a theta there, not an x. That's why I do my triangle up there. Okay, I'm getting ready to write my final answer here. So that's good because I'm almost out of room. I am out of room. 25 halves, inverse sine, x over 5 minus, so sine theta. So sine theta is x over 5 times cosine theta. Cosine theta is adjacent, right, over hypotenuse. So square root 25 minus x squared over 5. I could absolutely make that look prettier, let's see, but I'm out of room. Okay, and since I'm out of room, I think I'm going to grab a new sheet to do this next problem. So let's go ahead and we're going to take a look at integrating dx over 9x squared plus 4 quantity squared. So this is the only one with a plus, right? If we look at our strategy, the only one with a plus is the tangent. Okay, the other two both have minuses in them, and it just depends on who's first, the constant or the variable. So this is going to be a tangent, but notice my x, it's not just x squared, it's a 9x squared. So how are we going to deal with that? What should we do? It would be sure nice if that was just an x squared and not a 9x squared. So I think what I want to do is go ahead and factor out the 9, but it's not just a 9, it's a 9 squared. So I'm going to factor out a 9 squared out of this denominator. So let's come over here. I'm just going to work on that fraction. So I have, actually it doesn't even have to be a fraction. Let's just work on 9x squared plus 4 squared. I want to manipulate this so that I just have a single x squared here. So I'm going to factor out a 9. So x squared plus 4/9. All of that's still squared. So now I have a product that's squared, so I can square both parts. So that's going to be 9 squared times x squared plus 4/9 squared. Okay, so I have my x squared. That looks good. This is equivalent to what I have there. So let's go ahead and come on up here, and we're going to rewrite this so that I have dx. I haven't done any trig substituting. I've just done some manipulating. So this 9 squared's on the bottom. So I'll do a 1 over 81 out in front. And then I have x squared plus 4/9, and then that whole thing is squared. Okay, I'm ready to do some trig subbing. So I'm going to let, so when it's plus, x equals a. So careful, because it's a squared. If you look at the pattern, this 4/9, I don't want x to be 4/9. I want it to be the square root of that. So 2/3 tangent theta. And so then dx is going to be 2/3 secant squared theta d theta. To get my triangle, I'm going to go ahead and manipulate my x equals line a little bit, and I'm going to solve for tan theta because that's how I want to draw it. So tan theta is going to be 3x over 2. This is what I'm going to use to draw my triangle. So grab your theta, which is an angle, label the sides. Tangent is opposite over adjacent. Use Pythagoras to get the missing side, which, right, should look familiar, right? It should be part of your integrand. You say, oh gosh, look how that showed up. Okay, take a deep breath. Here we go. We're going to now make our substituting, right? So dx gets replaced with this, 2/3 secant squared theta d theta, and x gets replaced with 2/3 tan theta, and then we're just going to hope for the best. Here we go. dx. There it is, 2/3. Okay, all my coefficients I'm going to go ahead and move out front, and they're just going to get ugly. So 2/3 there. Secant squared theta d theta. On the denominator, I have x squared, which is 4/9 tan squared theta plus 4/9, and all of that's squared. So, oh my gosh, so 2 over 243 integral secant squared theta d theta. What do we have on the bottom there? So Pythagorean identity for the denominator, that's going to be a 4/9 secant squared theta squared, right? So it's just a little version of the Pythagorean identity, tan squared plus 1 equals secant squared, and it just has that extra 4/9 on it. Okay, so again, the 4/9 squared, it's in the denominator, it can come on out, it's going to get flipped and multiplied. So I'm going to get 81 over 16 times 2 over 243. And then I have secant squared theta d theta. And on the denominator, I have secant to the 4th theta, right? Secant squared squared. So go ahead and reduce. So I have, oh my gosh, I don't even want to try to do that kind of math right now. Oh gosh, okay. 8, I'm pretty sure that's just a 3. Yep, okay, so I've got 1/24 integral d theta over secant squared theta. Okay, breath. Now, secant squared theta, right? Maybe your brain's running to, oh my gosh, isn't that just tangent? Yes, but only if the secant squared is in the numerator. It's in the denominator, so that means that's not available to us. So right, you're running through your strategies, and you should get yourself to a place where it's like, oh yeah, that's right. Secant is 1 over cosine. So this is cosine squared theta d theta. And then we go to our double angle formula. So cosine squared, here's another identity, put it on your list. 1/2 1 plus cosine 2 theta. So now I'm going to get an extra half, so I'll have 1/48 integral 1 plus cosine 2 theta d theta. Here we go, I think we're ready. So 1/48 theta. We'll do our little u sub on the fly here, plus 1/2 sine 2 theta. And now we need to get back to x's. Okay, that's way back here. Okay, so here's my tan theta is 3x over 2, so theta is going to be the inverse tangent of that. Inverse tangent, 3x over 2. And now I have, oh gosh, I still have that sine 2 theta. So do you remember what that was? So 1/2 times 2 sine theta cosine theta. So now I just have to do plus sine theta. So remember, this is why we draw the triangle, so we can just look up here and pick that up. So sine theta is opposite over hypotenuse times cosine theta adjacent over hypotenuse. Oh, it's the same. Okay, that means I guess I have to do one more tidying step. I can't leave that one alone. Okay, final answer. 1/48 inverse tangent 3x over 2 plus 6x over 9x squared plus 4 plus c. Okay, so something I want you to keep in mind, if you're feeling, I was going to say bored, if you're feeling burly in your differential calculus ability, we just found the antiderivative of 1 over 9x squared plus 4 squared. And we found that answer to be, right, what I just put in a box down here. So the fundamental theorem of calculus says, hey, if I differentiate this expression keeping in mind some chain rule when you differentiate inverse tangent, we should get back to your integrand.